Okay, so since we're kind of having some issues with the offsets being inward and outward, that's fine. I don't have an answer for that one. I've yet to figure out why sometimes it goes in, sometimes it goes out. But the good thing is this is actually a problem anyway. So I gave you just a quick way of breaking this thing down and subtracting it into a truss, right? But it's not proper because this arm or this chord is not the same size as this chord. So I am going to go through the process of using positive and negative extrusions with you so that you can create a truss that has the same size for every member or a controlled size for each member. So first and foremost, the how do I want to put this? The fact that this is a straight truss is very, very important. Okay, the fact that this is a flat panel determines a lot about how you do this. So let me just put that out there as a disclaimer, because how you're going to do it with warped surfaces and stuff like that gets a little bit different. So anyway, the path that I would start to go down with this is to isolate each particular member and extrude it in two directions. So I'm going to extrude it in the Z direction, so kind of away from the panel in the positive and negative direction. And then I'm going to take that surface, find its normal, and I'm going to extrude it in the positive and negative direction that way. Now that's going to prove kind of challenging in this corner because we need to account for well, you'll see the errors that we kind of have to deal with. So let's go back to our lines, and those are going to be here and here, and these are our, oh sorry, not that, and here. And let's see, our top and bottom line are going to be this one, I believe. Yeah, that should be our top. Yeah, that's our top. And our bottom one is going to be the original curve. That's this one right here. So for all four of those curves, I'm going to make a wireless connection so that I can kind of start over from them. So I'll go to params and just do curve here. I'll call this one bottom chord. Well, you just call it bottom. Bottom curve, something like that. Make this wireless and pull it down. Then I have my top curve. That'll be this. Make it wireless and pull it down. I'll do the same thing for these. Name them appropriately. So this one is going to be origin bias curves. And the next one I'm going to call end bias curves. Alright, so here I have my bottom curve, my top curve, my origin bias, and my end bias curves. So these are going to be what I'm basing this exercise off of. And so let's actually start with the top and bottom, because they're going to be a little bit easier. These are going to be z-axis based, and yeah, I mean, they're just going to be z-axis based, so they're super easy. So let's just start with the bottom curve, and we'll have to do a curve and extrude, surface, freeform, extrude. And we're going to need the vector of unit z. So this is our direction. We just have to define a magnitude. And so, oh, also, before we proceed here, turn off everything from the previous exercise. That way you just have the framework again. So I've got to give this thing a slider, and it's going to be feet based. So I'll say 0 less than 1.00 less than 2. And then plug that into D, and then the bottom curve gets plugged in here. So you can kind of see right here already some of the detail that we need to be concerned with when we're doing an extrusion-based operation. So just be aware that we will have to kind of clean up some of these details in some cases. So then the other thing I have to do here is find the surface normal and then use that as an extrusion factor. So since we're operating in the z-plane, you would think that we could just use the y direction, but just because the z-plane is a constant doesn't mean I can't take my curve and move it this way. So if it's off plane, you can't really do that, and you still want to use your normal. So normals are what we're going to need here. So let's go and grab our custom tool, which we created earlier. You also have this on your toolbar, right? It doesn't it doesn't redo your Rhino every time, right? You don't know? Go to the user menu. I had you all create this. You don't have it anymore? Wow. Yours is there? Oh, okay. All right, well, maybe we just have to make sure that we're properly saving it. All right, so in that case, since you all don't have it properly configured, let's go and find it again. So we'll go to Analysis, and remember the 3 things you need for this tool are Area, and then Evaluate Surface, and then Surface Closest Point. So these 3 look kind of like this. The extrusion gets plugged in here. That's how you find your centroid or center point. The point input gets plugged into the point, or the centroid output gets plugged into the point input of surface closest point. The surface is the extrusion. The surface is also the extrusion here, and the UVP plugs into UV. So this is that golden normal group. Okay, so from that we have our normal, and so we can use that in order to do our second extrusion. So I'm going to grab the extrude tool again under surface freeform. I'm going to do extrude. And the direction is going to be, this time I'm going to use amplify. So under vector, vector, amplitude. And be aware here that the vector is obviously going to be the normal. The surface is obviously going to be the extrusion, and I have to define the distance. So this part is going to be up to you whether or not you want it to extrude just one direction, or if you want it to extrude on both sides. For me, my amplitude is going to be dependent upon extruding to both sides, and so my amplitude, I'm going to try to set it up with a domain so that it has a positive and a negative at the same time. I think I can do that. I think I've done it before. So under Math and Domain, I'm going to construct a domain on amplitude. So right now that domain defaults to 0 and 1, which is the same default that was on there already, so you wouldn't see a change. But we should be able to, and I'm going to do this with static numbers here. we should be able to plug in basically what positive and negative value we want to define our domain. So if the thickness of the bottom chord is going to be 1 foot, I can just put a value of 1. And then I'm, yeah, well, yeah, 1. Yeah, we'll do it. I guess it depends on how you want to think about it. So if you know that it's going to, if you're in good upkeep with your file and you know that half in this case is going to equal 1, that's good. You could just put half here. Or you could use, you know, this right here. You can make your value of 1. You can pass through. You don't have to do this, guys. I'm just throwing this to you as a label sort of thing. So you can drop a number thing in here and you can call this bottom thickness. And then you plug your 1 into it. And then you can put an expression. Yeah, I would pull it all the way back here. Make that wireless and then put an expression on it. For divided by 2. And that's just if you're going to do the domain on both sides. You don't have to. So that way, you know, this can sit back here with all of your other input values, and all the processing information can kind of float out here. So you have your bottom curve, you have your bottom thickness. Right, that makes sense. So then over here, your bottom thickness is split in half, and so you make your minimum value is going to be the negative. So I'll go to math operators, make this a negative. And then your maximum value is going to be the positive. Oh, it didn't actually do it, huh? 0.5. I thought that worked. Hang on, I think there's a way to do this. Just a moment. Okay, so from what I'm finding, I thought that there was a way to get domain to work both ways, but I think it's only with two-dimensional geometry. For instance, like a rectangle, you could use a domain for your x and y size. But essentially, if you just get rid of that domain, you can still use the same function. You're going to have to extrude it on both sides, so it'll be two separate extrusions that you'll then have to join. So we can put our negative in to A, and it's going to look like that, and then you put your positive in by holding Shift. And so here you have two extrusions that you can then join into one. So you go back up to intersect, and you can do a solid union on a set of B-reps. And so you should be able to take those two extrusions, plug them in, and then when you turn this one off, gave you a closed B-rep, but wait, what am I saying? Let me turn these off. There we go. That looks right? Yeah. Okay. Correct. So this gives you a solid union, but be aware that this is a Rhino function, guys. For those of you who know Rhino, when you do a Boolean join of two surfaces that are flush with one another, it retains the trace profile of the surface that overlapped it. So that's what you're seeing here. This line that goes down the middle is the trace profile of the intersection of the two surfaces. So you have to do what's called a merge all faces in order to get that to go away. And I totally forget where it is, so I'm just going to search for it. Merge faces right here. And this is in Control-Shift and click. It's under Surface and Utility. So once you plug this in, it takes that union and makes it one solid thing without that extra line. I'm only giving this to you in case you want to have it, be centerline based. Okay, so there are many instances where it must be centerline based, but also for a lot of academic exercises it doesn't have to be. So I'm just giving you these options here. Surface utility. Okay. So are there any questions on that so far?
The bottom thickness. Where
This?
I wasn't even. Yeah, where did you go?
Okay, so what I did was I created a wireless connector that basically just passes that information as a number 3 times. So if you think about it, it's really just a way for me to isolate this information off to the side, and then let this stuff, kind of do its work as an idea over here. So basically, I took a panel, I plugged it into one of these. It's a number. I renamed it to say bottom thickness. And so since this is an empty param, it just takes that number 1 and created a wireless connector to this. And this is the same thing. It's a number param, but it has an expression on it. So the expression, the reason I did the wireless connector with both of these is because the expression is to divide it by 2. Because my value of 1 is supposed to be my overall bottom thickness. But the divided by 2 is so that it goes to either side halfway. Yeah. So that's the centerline based function. Okay, so I'm going to stop this video here and make sure you're all caught up before we continue.